Great. Yeah. Thanks, Ryan, for the introduction. So yeah, Matthias and I will give you a little bit of an overview what openEO is now, and then also in the end relate this to Pangeo and maybe find some common ground there for future work together. Both are open source activities and development, so I think there's quite a lot in common. You will also see this now from the slides. So why do we need openEO? And also here I saw, actually I checked a little bit out also the Pangeo page earlier today, and I see that you also are aware of many of the issues that are out there with existing cloud platforms and computing solutions for Earth observation and geographic data analysis. But just to give you some example here, so all we want to do as researchers or data analysts is do our data analysis, derive some graphs, interpret them, derive some maps, interpret them, and so on. Of course, for this, we need to have access to data. Data access, however, is quite often organized very differently. It could be just very simple local file system or network drive or something like this. Could be a little bit more abstracted view on it in form of a data cube. Could be some kind of cloud-based API like S3 or something like this, object store to link with it. And when you do your code development, that means that for each of these solutions, you also need to develop different interfaces to utilize them, and which makes it also quite hard to transition from different service providers or the data centers for updating your code flows or your work. And every time you do that, you have to basically develop from scratch. And if you work with multiple programming languages in your team, then this just multiplies and becomes more and more complex. So here is clearly a need for standardization, and that is where the API comes into place, and where we started working on openEO quite a few years back already. I think we started in 2017 with the development of this. And initially, we thought it's a lot about defining the API and how to interface with it. In the end, this makes the whole situation a lot more simple, because now for each component, you only one time need to implement a software solution, and then you can use that, especially if it's open source. You can also share it with others. While doing this work, we actually realized that, like, defining the API is actually much less work than implementing the API in a lot of different scenarios. So for different client libraries here on the top, and different backend solutions here on the bottom. But since we are already working on this for quite a few years, there are quite many solutions already out there that can be utilized for this point. There are also other issues which I will, for sake of time, go not into detail, with related to data management, parallelization, code optimization, and so on. But you can see this, for example, in the EASY presentation in more detail, which we discussed earlier before. So how does processing in openEO work? Again, we want to do our data analysis. We need our data. In order to interface with that, we have clients. So in openEO, we currently support R, Python, and JavaScript. In order, the view on the data that we have is a data cube, a virtual data cube, actually, just so that you have the possibility to see a series of images as a collection, instead of needing to write code to access every individual file and so on. That's all taken care of by the library. Data cube has multiple dimensions. Here, for simplicity, I show only 3, X, Y, and T, or east or north, or lat and long. Doesn't matter. It can be even more dimensional. Actually, openEO is not fixed on these dimensions. For each point, you have your feature space, actually, which could be your different bands from your multispectral image, or your different polarizations from your SAR image, or whatever other feature space you have. Your different climate variables from NOAA, ECMWF derived climate data, something like this. Could be anything. Then, in order to make it possible that different clients can work with different backends, we need to have some layer of abstraction here. And this is the so-called process graph that we have in openEO, that helps you with things like data selection and defining what kind of data analysis you want to do without actually implementing that and directly executing it, because we have this process graph in the middle. So what you will do with the clients, and you will later see this by examples from Mattia, is basically you generate this graph which describes what you want to do in an abstract way. And once you have done this description of what you want to achieve, this is going to be sent to a backend infrastructure, which then takes care of things like job management, with multiple people send their requests, parsing the actual graph to understand what you want to do, and then transforms this into something that can be executed in an execution engine that can be any kind of software stack that can help you with doing the processing that you need to do, and is usually solved on the backend side. And finally, it also allows you to access your results in the end. Since this is all on a virtual layer, one of the nice things of openEO is also that you can convert your results to different file formats on the fly in the end of your processing chain. So we are not forcing you to only use GeoTIFF or only use, I know, JPEG images or NetCDF files, but depending on your needs, you can put your results out, even also just as a text file, CSV or JSON object or something like this, depending on your needs. Yeah, now I give the word over to Mattia.
Thank you, Alex. So we defined then the openEO API basically. So that is an HTTP JSON API. So that is very similar to, for example, what OGC APIs do with their APIs, except of course that we have a different way of processing. So OGC API processes is not part of it, but it's aligned with many other OGC APIs. For example, the OGC API Commons basic layer, then the features API, etc., and of course stack. The areas covered by the API, first of all, are of course data discovery. You need to know what collections are available, and also the process discovery and management. So you can, a backend implementation can define processes that are implemented, and then based on that, you can basically make your own reusable user-defined processes again and reuse them as if they were predefined by the backend. And everything, all of the processes are centered around data cubes, basically. Our definition of a data cube might be a little different than of what you're used to. I think when we are calling it a data cube is something that you call in X-array, if I understood it correctly, a data array. So it's not having multiple variables, but each variable basically is a single separate data cube in here. And then the other parts of the API that are included are user authentication via OpenID Connect, basic account management, and you can also upload your own files or data so that you can use that in your processing chain. And there are different ways of processing the data. So 3 ways basically. That is, depending on how you make it, it's for, but the first one is batch job processing. Simply submit your process graph that Alex has shown before, and then it's running over a certain amount of time. That's mostly used when there is larger processing time needed. And you can share the results and access them via different means. All of them, that is at the beginning shared via stack catalogs, basically, and then you can do whatever you want with it, ingest it somewhere else, for example, in Stack or so. Then there is on-the-fly processing via web services. So, for example, you can expose a WMTS based on top of your process graph, and then whatever you see on your map, basically, is just processed for you in the correct zoom level, so that you only need to really process what you're right now looking at. You can also expose other OGC APIs or different APIs that are not standardized by OGC, like WCS, OGC APIs, or XYZ. And then there is also synchronous processing, which is basically just you send it, wait for it, and it just returns it in the same HTTP call for short requests. UDFs can be added into the process graph. That is, you can run custom code basically, so that you're not restricted to the processes that we have predefined. We talk about the predefined processes in the next slide, but you can also just run custom code, like something that you have written in X array or 4 X arrays. You can transfer into the backend as well and run it. Some extensions are available as well to the API that came later and is more specific. But for example, the order extension for archives and commercial data, so getting things from an archive when it takes longer to get that, then this is the extension for you. Then it will be prepared for you and you can access it. It's a normal stack collection, similarly for commercial data. And then the federation extension is a thing that is for if you want to expose one or multiple implementations as one instance, like for example, openEO platform does for the Vito URAC and Vito EODC and Sentinel Hub backends, you can use that extension to show what is exactly available. And then the processes, we have a couple of processes predefined. These are centered around data cubes and allow all the operations that you need to do, like data cube analysis, basically. You can remove dimensions. You can apply over a specific dimension. You can apply over all values in your data cube. You can do mathematical things. Yeah, and also very specific things that are specific to a domain for climatology, for EO, whatever. And these are specified in a schematic way so that whatever you have on your backend implemented, the clients can read that and can make use of these schemas so that you can get a very customized way of working with them. So if some functionality is not present on one backend, the clients get aware of that and will not offer that functionality to you, so that you really can have a variety of implementations and you don't need to implement everything that we've predefined. And the process graph that Alex has spoken about earlier is basically something that is built by the clients and then sent to the backend. And then it's executed in different ways. Usually you start with something that you want to do with your data, for example, executing or computing an EVI, and then you just want to go to whatever client you have, insert or have the formula inserted into your editor. And then you can do that, for example, in our web editor, which is a web UI, or you can do that in Python or R or JavaScript in a native way, basically just using the normal math operations in your programming language. And that's then get translated to some, it looks a bit confusing and weird, but that's basically the schematic graph representation of this formula in openEO. You don't really need to care about that, but mostly using or generated by the client, so you don't usually look at that. And that's then inserted into the broader context, into your process graph data cube operations. For example, an EVI computation over 3 bands that results in single values is a reduce operation for us in openEO. You would do that on the band dimension. And then you have basically, if you have X, Y, T bands beforehand, you would just have X, Y, T, everything computed. And here in the process graph, you should just like load at the beginning in the first node the collection, make a monthly composite of it, then reduce over the band dimension and save the results to geotiffs. And that can be done in all clients. For example, we have a JavaScript client and based on that, the browser client as well. So you see the same process graph here that you had before, and then you can run it. It gets visualized as geotiff on the right side on the map. You can click on single values and you see that there is like the yearly way of how like the vegetation is usually growing. You can manage your batch jobs, etc., all in a nice web UI. And then you can also switch between the clients. For example, you like that, but you're more into Python, then you would go into the Python client. You can write the same code. Basically, you would start connecting to it. Here to open your platform, you can do some things in the Jupyter lab. You can first like go into different collections of processes, visualize them in the Jupyter Lab, it always renders nicely and is well integrated, shows like the HTML view and not just the JSON that it got from the API. And then you would want to write the same, for example, in Python. And then you would just write your Python code here. You see that it's basically the same. You have 3 parts. Again, you would do the load collection with all the parameters, spatial extent, temporal extent, etc. Then do the aggregate temporal period for the monthly aggregate. Then do the reduce operation with the formula that you've seen before. The EVI, basically the EVI computation for each of the bands, you have make a variable, and then you can just use the normal math operations, and then save it as a geotiff. But if you don't like Python and you want to go to R, then you can write the same code in R as well. You see it's it's the same. You connect to it. You can do also integration it's well integrated in RStudio. You can do the same as you did before. You can show the processes or collections. It will then show up in the right lower pane. What's available, you can look at it. And then you would want to do the processing again for the same thing. You construct the process graph. You again do load collection with the temporal extents. A monthly aggregate, do the reduced dimension with the formula that we have for the EVI, and save it again. So that's all the same. It's looking all the same throughout, just made look native to the individual programming languages. You would get the same processing graph in the end. And if you submit that from the R or Python client as well, you can also go to the web editor back again, and the job would be running there, and you would see it, so that you can simply switch between languages. And a person that is working on it, for example, that is Python aware, can do that, and then his colleague who is R aware can also look at it or work with it. There are easy ways to convert between languages as well. And then the next slide is Alex again.
Exactly, yeah. Thanks for the overview of the different clients. Now I will just give you a very quick use case example that we had in the end of the original openEO project in 2020. For example, in this case, we wanted to calculate the areas of wet snow in mountains. For this, we needed to know where snow is. And then in order to understand if the snow is wet or dry, we use radar data. So these are 2 collections that were available in the backend that we were using at the time. So these we can utilize then we can start using openEO for the simple data access, which I've also seen that some people working with Pangeo have already done in some of the tutorials. So basically just using openEO as an access tool. It's kind of underusing, however, what you do, because you can do a lot of the processing directly in the backend as well, which basically reduce a lot the overhead of downloading stuff, especially if you start downloading huge collections like Sentinel-1 or so from a different place. So you can directly in openEO also use the standardized processing as presented by Matthias before to do all kinds of mathematical operators and a lot of more complex functions by now as well. This catalog is steadily growing. I think by now we have 120 functions or so defined, and this goes always forward. In this case, we needed to have a reference image defined, and then the difference from this reference image in order to understand if conditions change, or to understand if the snow might be getting wet in SAR data. Basically, SAR data cannot see the snow as long as it's dry, but as the more moisture content is creating in SAR, then the more it becomes visible actually as a change. And this way you can see that this wetness change is related to snow, because we also have the snow masks. For this masking process, we do a kind of classification then, where we use the information from the modest snow maps that we have generated, and then basically cross-check that with the status of the Sentinel data. In this case, we did this by now using R as a user-defined functions, where we just simply piped a custom R script in the processing chain to do this simple thresholding and task. And finally, you can then download your maps to your local environment, and then do nice things like create a GIF or whatever out of it. Here you can just see the melting process of the snow over time. So the more we go towards spring, the wetter it becomes. You can see basically from here when everything is melting. And then in summer, there's basically no snow left unless in very high altitudes. Small example. Going back to the technical stuff, so I give you a quick overview of one backend, the one that we have here at URAC, which is a relatively simple backend meant for our research institute here. What we do is basically we have all of our data in data cubes, but already for historic reasons, we have several data cube systems, which has quite some complexity, and even internally we have some heterogeneity because of this, and different people who want to access different data cubes need to write different codes. So then we started to develop this openEO driver here, which can access the different data cubes, be it from Rasterman or exposed to the Open Data Cube through the same interface, so that now our researchers can work in their programming language of choice, and they don't need to know anything about the actual technical infrastructure that we have. The nice thing with this level of abstraction again is that in future, if for some reason Open Data Cube or Rasterman is not a good software anymore, then we can exchange this, and from the client perspective nothing changes as long as we update our driver software here in the middle. Then there's also the part of the UDF environments. So these are basically separate sandbox environments for security reasons, where we can execute the user code that is piped into and evaluate it, and then continue back to the processing chain in the openEO drivers. To explain this a little bit in more detail, so openEO in this whole part is basically the glue that brings it all together. So we have the openEO library that links through the RESTful API clients to the backend. It helps us to generate the process graph, send it to a backend, where it then can be translated into a, for example, traversable Python object if the backend is Python based. And then we can run functions like load collection to load our data set. These data sets refer to some kind of data cube view. So this load collection function that we have implemented here is working on top of Open Data Cube and relies on that. Open Data Cube is basically our index database that knows where all of our remote sensing data files and many others as well are located, and exposes them as a virtual data cube view, and conveniently Open Data Cube is also based on top of Xarray, which makes it quite easy internally in our backend to hand over in memory the loaded data to our processing engine, which we have written then in Xarray, where we do all the heavy lift processing. Xarray, again, due to its definition, is easily also parallelizable with libraries like DAS, so that you can scale it out and make your code more efficient over a large cluster. And I take it that many of these tools are quite familiar to the Pangeo community, because I think I saw them frequently mentioned also in the Pangeo software stack. And I think there's also a good deal of overlap and collaboration potential, especially on backends that are based on this particular kind of software stack. But as I said, the nice thing with openEO is this is only one possible solution of implementing a backend. There are many others as well, which you can find also on openEO GitHub, where all the different backend implementations are. So basically, there are a lot of things that can, I think, work together there. These first technologies I just mentioned are a starting point there. We had some interesting discussion recently also on our issue tracker regarding integration of some new Xarray APIs. I don't know if the person who put this is also here today in the auditory. That is, there might be some things possible there. Generally, the work on the implementation of the processes could be a lot of common work as well. I mean, right now, as I said, we have around 120 processes, and not all of them have yet been implemented in Xarray, and there are many more things that can be needed also in the future, which could be implemented together. So a common catalog of functions that can be used for EO and geo compute that can then be either used in an openEO backend or just in a plain right X-array environment for processing could be a nice idea there. Then again, the software stack is quite useful in a particular group of backend implementations that are based on top of X-array and DAS. There are a few different backends that work on this. I know 3 different ones right now that use this particular solution, the one that we have here in Europe, the one at EODC, and then another one in Sweden from RISE. We are also currently working on wrapping this particular backend solution as a kind of ready-made Docker container, so that people can have this as a mini backend directly in their own environment, be it their own computer, workstation, or cluster for testing out and playing around with openEO. It's a relatively straightforward and simple backend. There are other backends which are based on top of Hadoop or Spark cluster or other software solutions, which are maybe a little bit more complex for people who are not so used to these environments. The next advantage, and where we can maybe also help Pangeo, is that we are reaching a lot more than just Python users by having this abstraction layer. So really linking to also other communities. For example, we work a lot with people also from climate community, and many people there, at least here, are using R. So for them, they're always quite happy that they can continue to use R for their analysis. Then also when working with openEO. There's also some part linked to fair processing, fair data. When having these process graphs, we always store them. You can share them later with other people also, which helps with reusability and again for the abstraction layer also transferability of your code, so you can run them in different openEO environments. And finally, also in terms of documentation and tutorial work, I think there are lots of things that we can do together. I'm referring here also to a nice document that I've written together with Ryan for a particular client, which was the European Commission, that wanted to know how to improve the Copernicus Global Land Service to a cloud environment. And many of the things that we are developing, both in Pangeo and openEO, are quite interesting and also mentioned in this document for how to set up a cloud environment on a large scale. And I think there are quite a lot of synergies from our side. So where are we now going to wrap up here? So further improvements for the federated implementation. So right now we are heavily working on this part, really how to bring different clusters that have already an openEO environment there and bring them into one federation, which makes it easier for large scale processing and also cases where not all the data is available in all the backends, but if they're all part of a federation, you can start sharing things and exchange. We have also other more technically challenging things like linking not only or working well with raster data, but also with vector data and working on the concept of vector data cubes and how to integrate that into openEO. Machine learning extensions. We started with simple classical machine learning things like random forest support vector machine, but maybe want to go also more advanced and more capable deep learning applications as well, where we need to have a whole different frameworks of how to define your models in a standardized way, exchange models, pre-train models, link them to your processing chain and so on. Further linking to also OGC, we are considering right now if it makes sense for us to become and try to become an OGC community standard, since there are now quite a lot of implementations around there. So we are in touch with them as well. As said, we are really hoping to also collaborate with you guys here. I think they do a lot of nice work as well, and there are a lot of overlap that we can link to. The local processing we are working on right now, so that there's a kind of thicker version of the Python client that can do processing without having a backend by loading directly the X-array based processes locally for testing, and then later when you have defined your workflow, send it to a big backend for large scale processing. The Docker container already mentioned. Yeah, the number of backends is constantly growing. When we speak of backends here, we mean really services that are operated operationally and are available, around 10 or so now. Now we are also in discussions with, for example, Microsoft Planetary Compute And let's see where this leads. We had some exchange with other Open Data Cube based backends in the past as well. Yeah, I think this was the general overview for today, and hopefully can spark some nice discussion now. So really thanks a lot for all of you coming here, and we are ready for questions and discussion.